Welcome to the this week's Storms, Eddies and Science session. I will advertise at the end. The next one is on the 18th of November, which is a kind of machine learning special for Storms, Eddy and Science. But for this week, we have three excellent speakers. Amanda's going to tell us about the North Atlantic mean state in eddy-resolving models. Benoît is going to talk about eddy variability and sea level changes, and then Michael, who's in the room here with me, is going to talk about AMOC at different resolutions, comparing our model with observations. Okay, so with the speakers, I will try and give you a shout at about 12 minutes, and then I will cut you off at 15 minutes so that we have 5 minutes at least for questions for each speaker. Okay, so Amanda, please fire away.
Okay. So I have compared 4 coupled eddy-resolving models following the high-resolution protocol with 39 also coupled but only eddy parametrized or eddy permitting CNIP6 models. I'm going to call these two ensembles the high-res HIST and low-res HIST ensembles during the presentation. And as model selection criteria, so I took the models that had temperature, salinity, and AMOC available from monthly output. The study period was the period 1980-2014, and we looked at one member per model. Some details about the models that I used. So the high-resolution models are CESM1 CAM5 SEHR, ECR3P very high resolution, HGEN3 GC31HH, and also MPI ESM12 ER. And all these models have a nominal resolution of 10 kilometers in the ocean, so horizontal resolution. And they use different components. We have top 2 MIMO, also the MPI ocean model, and then regarding the atmosphere, there are also a wide range of components, and the resolution ranges between 16 kilometers and 100 kilometers. Regarding the low resolution models, so mainly they have a resolution of 100 kilometers and in the ocean, and in the atmosphere, usually the resolution is between 10 and 100 and 250 kilometers. We started looking at the sea surface temperature biases, and we used EM4 as observation of reference. On the left panel, you can see the individual models. The last row shows the high-resolution models, and on the right panel, I show the ensemble means. So we have the low resolution ensemble mean. We have this warm bias by the coast north of Cape Hatteras, and then a cold bias in the central North Atlantic. And we see that at increased resolution, these biases are both reduced. On the other hand, we have a strong warm bias in the Labrador Sea. And for the sea surface salinity biases, we have a similar pattern. And so a positive bias north of Cape Hatteras, and then a fresh bias in the central North Atlantic. And again, at enhanced resolution, these two biases are reduced. And we have a salty bias that appears in the Labrador Sea. We also, we zoomed into the Labrador Sea. We looked at the vertical profiles of temperature, salinity, and density there. We found that, so I start with the colors. The red thick line shows the high resolution ensemble mean, the gray line shows the low resolution ensemble mean, and the black line shows EN4. And so we found warmer conditions in the upper 100 meters at enhanced resolution, at high resolution, and below that depth, then it's the other way around, that high resolution is colder than low resolution. For salinity, also, we have saltier conditions at high resolution compared to low resolution in the upper 150 meters. And for density, we see this reduced stratification at high resolution, which is caused by an increase in density in the upper 150 meters. And this increase in density is caused by increasing salinity in the surface. It can come from the temperature, this increase in density, because we have a warmer surface at high resolution, which would mean less dense waters. And then we also compare these profiles to how they compare to observations. So here on the x-axis, I show the vertical correlation coefficient of the different models with the EN4 profile. And on the y-axis, which is the distance from the vertical curves to the EN4 curve. So the vertical model curves to the EN4 curve. This for temperature, salinity, and density. And we find that for temperature, the vertical correlation is improved at high resolution. So again, red is high resolution and gray is low resolution. The vertical correlation is improved, and also the distance to the EN4 curve is reduced. For salinity at high resolution, we also have an improved vertical correlation. And for density, again, we have an improved vertical correlation to the EN4 curve. And we also looked at mixed layer depth in March. We calculated it from temperature, salinity, and salinity, and we used the same method across all models and observations. The method was a density threshold method. And we found increased improved convection in the Labrador Sea and the Nordic Seas, and also along the Greenland boundary current, both the East Greenland current and the West. And so the values for high resolution are closer to the ones derived from EN4. We also compared our results to observational studies in the Labrador Sea. And for example, results from Holt et al. 2017 show that in the Labrador Sea, mixed layer depths go down to a maximum of 1,800 meters, which is a bit shallower, but in quite good agreement with our values for high resolution. And then also there's this other study, Yeshaya and lower, that shows the mixed layer depths of around 1,200, between 1,200 and 1,700 meters in the Labrador Sea. Again, these values are a bit shallower than ours, but still in quite good agreement. And what these differences come from, so observational studies are based on individual profiles, meanwhile our calculations are based on monthly model output. From models, it's easier that the profiles are smoother, and which gives rise to deeper mixed layers. We also looked at 26.5 degrees north, where we have observations from the RAPID array, and we found a reduced distance to the RAPID curve at high resolution. There are no outliers at high resolution, also the maximum is better captured at high resolution. And though what happens is that the AMOC is still too shallow as for low resolution compared to rapid observations. And then finally, we looked at the barotropic stream function to look at the gyre circulations. If you look at ensemble means, we have I show also this dashed black line. This is the zero contour line of sea surface height from observation. So it delimits the northern boundary of the subtropical gyre. So ideally, this should overlap the zero contour of the barotropic stream function. It tells you where the so if you look at the low resolution ensemble, you see that the Gulf Stream separates too far north from the coast, and this is this is corrected at high resolution. We see that it separates farther south, even a bit too far south if we look at the dashed line. But this southward shift explains why we don't have this warm bias by the coast at high resolution anymore. And also we see that the Gulf Stream is stronger and narrower, closer to reanalysis, and that we also see changes in the North Atlantic current path. We see that it is less zonal. So, for example, if you look at the green box, which is where we had that cold bias, at low resolution, we see that it's only touched by waters from the North Atlantic current at its southern edge. Meanwhile, at high resolution, the North Atlantic current reaches farther north, and it has a bigger effect on that area. And then another improvement is that we have a stronger subpolar gyre, which is more realistic if we compare it to the reconstructions from ORAS 5M, the reanalysis. Just to sum up the results, we have that at high resolution, we have reduced warm salty bias north of Cape Hatteras, which is linked to the position of the Gulf Stream separation, which occurs farther south. We have reduced cold fresh bias in the central North Atlantic, associated to an improved North Atlantic current path. But then we have this stronger warm salty bias in the Labrador Sea, which is a matter of debate. In the Labrador Sea stratification, we have an improved density profile, reduced stratification due to the salinity increase in the upper 150 meters. The mixing, we have a stronger mixing in the Labrador Sea, in the Nordic Seas, and along the Greenland boundary current. And the values for the high resolution, from the high resolution ensemble, are slightly deeper than those from observational studies. Then the AMOC is weaker for, I don't know if maybe I forgot to mention that, but the AMOC is weaker at high resolution. It presents a reduced distance to the rapid curve compared to low resolution. There are no outliers, but still it's too shallow. And the Gulf Stream is shifted southward, the position where it separates from the coast. It separates a bit too far south. It has an improved structure. It's narrower and the current is stronger. And the North Atlantic current has an improved structure and it is less zonal. And to finish, then the subpolar gyre is stronger and closer to reanalysis.
Great, thank you, Amanda. Perfect timing. Very nice.
Okay.
Questions, anyone? And I'm not completely sure I can see hands, so if you have a question, just shout and go for it. Anyone? So maybe I'll ask one. So it struck me looking at your the profiles in the first plot or the second plot that the CMIP has such a wide range of profiles in the Labrador Sea, from crazily kind of warm and fresh to or cold. I don't know, cold and fresh.
Let me go to the slide. This one?
If you look at that scatter in the grey, there's just such a wide range from the CMIP models, but we only have 4 high-resolution models. So I don't know, is there any way we can do the analysis? So you say the high-resolution models have no outliers, but there's only 4 of them. I don't know if there's any cleverer way we can suggest that the high-resolution models are, almost self-tuning, that they have processes so they get closer to the observations, whereas the low-resolution models, either some of those models are not very well tuned, or maybe they're much better elsewhere in the world and not very good in the Labrador Sea.
Yeah, probably. Yeah, I could do a test of significance. But you're right that it's hard to say that. But it's also true that these warm bias at the surface, all of the high resolution models have it. So it seems to be something exclusive from those. Meanwhile, in the low resolution ensemble, it may or it may not be there. Then maybe it would be better to say that this warm bias is not something exclusive from high resolution models. High resolution models.
I mean, it kind of is, to me, somewhat striking that those low resolution models have been, not unchanged for 20 years, but at least those kind of models have been around for 20 years, and they still have such a range. Okay, so Labrador Sea is a relatively small area, but still, Anyone else?
Maybe sea ice.
Yes, I'm sure. Yep.
Maybe also in that direction, isn't there a low resolution version of this high resolution models that you could see if they behave similar or if they have the same spread as these all 39 low resolution models, so that you see a little bit more if it depends on the model or on the small sample, maybe?
There is a low resolution version of those models. We didn't include those models in the analysis, but it could be done. Yes. We took this bigger ensemble. We took all the CMIP 6 models because it was a bigger ensemble.
Could be a good idea. Okay, great. Thank you very much.
Thanks to you. I'll stop sharing.
Thank you. So Benoît, if you want to share and go ahead.
So hello everyone, my name is Benoît Laurent, fresh second year PhD student with William Level and Marie-Thérèse and Antoine Rocher. And I will present today the contribution of internal variability to dynamic sea level change. Sorry. So we all know that sea level rise is a consequence of global warming, as the IPCC measured the global linear trend of 3.3 millimeter per year over 1993 to 2014. As we can see on figure 1, this regional sea level trends is obviously very different from the global similar trends, especially in the very energetic region, like the Kuroshio near Japan, the Gulf Stream near east of the US, and the ACC around the Antarctic. measuring the sea level change is very important, as it is a measure of both the thermal expansion and the mass apport to the global ocean. And therefore, it also has consequences of global communities, coastal communities, with 267 million people worldwide that live less than 2 meters above sea level. So, in my PhD, I observe dynamic sea level changes, more dynamic sea level trends actually, which is the trends of sea level above geoid. I use for that CMIP6 and the variable those with a few corrections. So first, I average it yearly to remove the seasonal cycle. Then I remove the global mean sea level to correct the boostiness assumption that has a global expansion term thanks to volume conservation. And finally, I use the trends over 1993 to 2014 to be able to compare it with the satellite observation. So within CMIP6, I use the model AGEM that follow two protocols, the CMIP protocol and the IRIS-MIP protocol, with 3 resolutions. So the LL resolution with 1 degree, the MM resolution with 1/4 degree, that is partially resolving eddies, and the 1/12 resolution, the HH, that is really just completely resolving eddies. So we have access in historical, so with initial condition of 1850 plus small initial variation, 55 member in LL for CMIP, 4 member in MM for CMIP2, and way too few for IRIS-MIP to make a good enough model. However, we also have access to PI control bands, which are 2,000 years for LL in CMIP, 500 years for MM in CMIP, and 100 years for all resolution in IRIS-MIP, that are more interesting if you want to study difference of resolution. So I use 2 types of ensemble. The historical ensemble, as we saw earlier, is too small to draw conclusion in most resolution except the low resolution for CMIP. But meanwhile, we also have the PI control ensemble, which is an artificial ensemble created by cutting PI control into 22 years pieces to make a format similar to the historical ensemble that can be observed. So if we take the mean of those ensembles, it can be approximated to the external forcing common with all the members of the ensemble, which is the external forcing response, either due to natural causes like volcanism or anthropic causes like aerosol of greenhouse gases. Meanwhile, if you use the standard deviation of this ensemble, which is basically how much each member of the ensemble differ from the mean, we have the internal variability response that is mostly approximated to be entirely natural. So similar studies have obviously been done. I chose a monomodel approach with AGEM. That means that the ensemble is made from a member from exactly one model, like for example, Frigola in 2020. But a lot of state-of-the-art use a multimodel approach with equal weighting of all models, assuming that all bases of the model will average out. This is still advised by the EPCC as a solution to low member count, but I didn't go that route because I don't trust the biases that will imply with it. It's a very so first thing first, we compared ensemble mean and ensemble STD of historical dynamic sea level, so the one we have 55 member for, over 1993 to 2014, on these 2 figures here. And we can already see a large trend over for the ensemble mean over the Arctic Sea and the North Atlantic Sea, with a large dipole of south of Iceland. STD, so internal variability. We can see the large trend in North Atlantic, Arctic, as well as around the Kuroshio and the ACC. So I asked myself, is the internal variability differ between PI control historical simulation, as it is an approximation often done, most notably in the multimodel approach. So here we have the PI control ensemble STD on the left, and the ensemble STD of historical mean on the historical runs on the right. And as we can see, it's very close to each other with a few outliers, but the approximation is mostly accurate. I also wonder if 39 members are enough to assemble to quantify HMLL internal variability. So we have the max number of members on the right, that is 55 members, and only 29 members on the left. No, it's the opposite. Anyway, the conclusion is that between the two, the difference is as well pretty negligible. The most important figures. So we have on the top the LL resolution, on the bottom the MM resolution. So 1 degree resolution, non-eddy resolving on the top, and 1/4 degree resolution, eddy permitting on the bottom. And with CMIP on the left and IRIS-MIP on the right. And we can compare the two of them, and we can see that two of them are pretty different. So we have a large difference in low resolution around the Atlantic North and around the ACC, most notably around the coast of the Antarctic, as well as a large peak on the Kuroshio for the CMIP that is not found in IRIS-MIP. Meanwhile, in medium resolution, the differences are way lesser, but we still have a larger internal variability for CMIP than for IRIS-MIP around the ACC. And the Kuroshio is way more marked on the IRIS-MIP model than on the CMIP model, which is way more in point with the observation. It has to note that the difference between IRIS-MIP and CMIP are multiple. Like there is a difference, if I'm not mistaken, on all the aerosols have taken. There is also a difference on the initial condition, as CMIP is taken with 1850 initial condition, and IRIS-MIP is taken with 1950 initial condition. So there are a lot of little differences as such. Finally, we observe the IRIS-MIP model within the free resolution. So this is on the top the low resolution, on the bottom left this is the eddy permitting resolution 1/4, and the bottom right this is eddy resolving resolution with 1/12 HH, with 29 members each over 22 years. And we can see that the difference are pretty impressive between the low resolution and the other two resolutions. From the low to the medium resolution, we can see the Kuroshio dipole appear. We can see some first trace of the dipole around the Gulf Stream. But in the higher resolution, the dipole around the Gulf Stream that is observed in the satellite altimetry is way more marked, as well as the ACC internal variability. It has to be noted, however, that it may also be due to the lesser number of members, as we have only sorry, I misread. No, so On the following of my PhD, I will study the HH control run of the CERI protocol in order to compare the two protocol and all resolution. I didn't do the calcul yet, but it should be done in a few weeks at most, I think. I also do a more in-depth study of external forcing and study the thermal and allosteric influences on sea level trends. Finally, I'll also study the different the approach of different model on sea level trends to see if the multimodel approach is interesting or not, and to see what type of ponderation it needs to be done in order to have something more physically accurate. Thank you for your attention.
Thank you very much, Benoît. Very interesting. Yes, very interesting. Questions, anyone? Maybe I'll ask an initial one. So I was interested in, was maybe your previous slide, that the Arctic sea level trends looked quite different between the lower and the higher resolution. So what drives the sea level trends in the Arctic? Probably I should know that, but
yes, I forgot to mention that. Yes, the Arctic is also pretty impressive.
Mm-hmm. So what is the likely difference in what's happening in the Arctic between the low and the high resolution models? Is that obvious or is that complicated?
You know, I'm not entirely sure, to be honest.
Right. Okay. Yeah, I'm just trying to think in my head, because the obvious thing to say is sea ice, but then the sea ice is complicated, right? In that the models often don't have the sea ice embedded in the ocean; it's kind of floating on top, which I don't really know that. Yeah, whether that relates to the sea level trends either. So yeah, I'm going to cause myself trouble to continue with that. Anyone else? I'll ask another one. Effectively, I think on your first plot, which was the observed trends, so the tropic, particularly the tropical Pacific, stands out really clearly. Is that related to the kind of trends in the surface temperature that we found over the last few decades, and it's been tended to be a cooling trend in the East Pacific? Are those sea level trends kind of following that, which the models are not very good at doing, or is it something else? Do you know?
I'm not entirely sure. Maybe also entirely due to endophenomena.
Okay.
I'm not entirely sure.
Okay. Right. If there's no other questions, thank you very much. That's very nice. And then, yeah, the third speaker is Michael, who's here in the room with me, and he's going to tell us about AMOC.
Today, I'll be talking about what the AMOC looks like in the HM3 GC5 model, which is being run for the EERIE project, and particularly compare them to the OSNAP and RAPID array. Oh, I spelled RAPID wrong. I did. Yeah, with many thanks to other people in the Met Office, and also particularly to Gökhan and Frederick from for sharing the metric package and the OSNAP code for the calculation used here. So the simulations that I'll be talking about today is the Met Office's contribution to the EERIE project. So Malcolm has been running 3 different resolutions of the same model. So the LL, low resolution, has 1 degree ocean, so it's Orca 1, 100 kilometer-ish ocean and a 130 kilometer atmosphere. The medium resolution is based on Orca 025. It's about a 25 kilometer ocean and 60 kilometer atmosphere. And the HH high resolution is based on the Orca 12. has a 20-kilometer atmosphere and 8-kilometer ocean. So I will be talking about the PI control today. So these runs are based on the CMIP 6-like control simulation, so it uses the 1850 forcings instead of the Harris MIP 1950 forcings. So as a quick overview, this is what the AMOC in depth space looks like in the two models, in the 3 resolution of the same model. So top row is the high resolution HH. The mean is on the left and the standard deviation is on the right. And the contour lines on the right is just the mean state again. So this is to point out that an increase in resolution leads to an increase in the AMOC strength. And in the standard deviation, where the most standard deviation happens, it's not the same place as where the mean state is strongest. It's slightly deeper. And you can see this effect a bit clearer in the density space. So in density space, you get, it's basically, instead of using the depth space, you convert it into density space. And this is better for the higher latitude regions, so 40 north onwards, where there's a strong east to west density gradient, and therefore in depth space you have cancellation between the northward and southward flowing current. So if you separate it into density space, you capture high latitude circulation a bit better. And you can see that again, increase in resolution leads to increase in the overturning strength. And also the interesting thing in the standard deviation here is that there's like a dipolar structure where the maximum standard deviation happens at this deeper level and on this lighter level, so at the kind of upper and return branch of the AMOC, instead of where it's strongest at the in the mean state. So where the variation happens and where the mean state is strongest is slightly different. However, it's difficult to compare this to the real world because we don't have these pictures in the real world. In the real world, we have a series of observational arrays across the Atlantic basin, the most extensive one being RAPID, which has been in operation since 2014. But in the OSNAP, which has been in operations from 2014, so about 10 years, has revealed very interesting results, which showed that most of the overturning actually happens in the eastern part of the basin instead of the Labrador Sea, which was assumed to be the case in the models because that's where the largest variability was. So yeah, the point of this study is to try and compare against the best sources of observations we have of the AMOC and see how our models are performing in those regards. So in terms of RAPID then, on the left is a time series of the volume transports. So focus on the green, blue, and red, and then ignore the rest, basically. So the green, blue, and red are the PI controls of green is the high resolution, red is the medium, and blue is the low resolution. And this black line is the observed range. And we can see that, as I said before, an increase in resolution leads to a stronger volume transport. And although the high resolution seems to be stronger than the observed range, bear in mind this is the 1850 PI control, so you would expect it to be slightly stronger. And more importantly for climate, it's the heat transport rather than volume transports which matters. So despite the green line having a stronger volume transport, on the right is the heat transport. the green sort of distribution actually matches the observed distribution better. So just to explain, the dots, the circle dots are the total heat transport, and the crosses is the overturning component, and the triangles are the gyre component of the heat transport. And it's on the x-axis is the AMOC strength, and y-axis is the Northern heat transport. So, for example, in the high resolution, although the volume transport is a bit high compared to the observations, the heat transport matches really well. In the medium resolution, the volume transport is more similar to observations, but the heat transport is a bit weaker. And in the low resolution, both the heat and volume transport is weaker. So we do see an improvement in the AMOC with resolution across the RAPID line. How about the OSNAP line then? How does the OSNAP line? Oh yeah, wait, sorry, yes. Also the RAPID depth profile. Again, only focusing on the green, red, and blue lines. We see that the green lines. Oh yeah, sorry. So on the left is the temperature profile with depth. The black is the observations, and the colored lines are the difference between the model and the observation. So they are kind of biases, or the closer the color line is to 0, the better it is, the better it compares to the black line, basically. And in both temperature and salinity, you can see that higher resolution models lies closer to the 0 line. Yeah, so there is a clear improvement in both the strength, the heat transport, and the stratification with high resolution at the RAPID line. How about the OSNAP line then? So just a reminder, the OSNAP line is split into a west and east component, and it's expressed in density space for the reason I said earlier. There's a strong density gradient up here. So the mean state is shown in the top panels, and the standard deviation is shown at the bottom. The colors for the different resolution is still the same. So yeah, in terms of mean states then, as I said before, you get an increase of the AMOC strength with resolution, and that's true in the total east plus west, in the east and in the west, in the west and in the eastern basin. However, it's quite a bit stronger than the observed overturning strength in all three expressions of the OSNAP line, and it's also similar in standard deviation. So the high resolution model is both too strong and too variable compared to the observations here. And yeah, again, you can see this sort of bimodal shape in the standard deviation that I pointed out earlier, where the mean state is strongest. It's not necessarily where the AMOC is most variable. There's slight differences in the process that control the mean state and the variability. And comparing the depth profile then, similar to RAPID, temperature on the left and salinity on the right, we see that in the higher resolution model, the green line, it's much warmer and saltier than the medium and low resolution model, and its biases or difference to observation is actually larger than the other resolutions. One thing I haven't looked at is whether these differences cancel out, because it's both warmer and saltier, maybe in density. It then has a similar stratification. But even if that is the case, difference in the surface sort of relative importance of temperature and salinity can affect how sensitive the overturning is to different forcings. So yeah, so the difference in the OSNAP overturning strength seems to be related to the difference in the surface biases. And as I pointed out before, overturning strength is not everything. The heat transport is also important. And we actually see that although it's too strong in the high resolution, in volume transport, the heat transport looks pretty good compared to the observational range in the high resolution. So how does the total heat convergence looks like then across the North Atlantic? So this is taking the heat transport across the RAPID line with the OSNAP line to see how much heat remains in the polar region. And in the low resolution, the color line is the OSNAP line and the gray line is the RAPID line, and the black is the difference. The convergence is much too weak compared to the observational range. And in both the medium and high resolution, the convergence compares pretty well with the observational range. And that's because the high resolution heat transport is stronger at both latitudes. So it's more heat going into the subpolar and also more heat coming out of the subpolar North Atlantic. So conclusions then. The volume transport and ocean heat transport at RAPID is improved at higher resolution, but at the OSNAP line, higher resolution is not obviously better. And the OSNAP differences are related to mean state biases, so too warm and salty, also a lack of sea ice, which I haven't shown here. Next steps. The biases and differences in HatchIMS3 are generally understood. They are similar to biases in the previous generations of model. So I really want to start looking at the other models to see whether they behave similarly. And the other aspect is, what is the large scale of climatic impact of the difference in the RAPID and OSNAP line? How important is it to get the OSNAP overturning right? How does that impact what the overturning at RAPID? How do the two lines relate, basically? That's all from me.
Very much. So questions?
Michael,
maybe I'm going to follow on from the first next steps you have. So it's interesting. So Amanda said from the 4 eddy-rich models that actually the AMOC got weaker at higher resolution, whereas I think whenever we run high resolution models with our model, the AMOC always gets stronger when we increase the resolution. There's the other models that happens in other models that apparently we've never seen, and that's really intriguing.
That's right. I think Amanda's results are quite interesting, actually, because it seems that high resolution has a slightly weaker but more realistic AMOC, but the range is quite a lot larger in the lower resolution model. I don't really think this sort of OSNAP calculation has been done in many other models, so it'd be really interesting to compare that between the HatChem and other models to see what really is happening.
Okay. Other questions?
Hi, Michael. Great talk. Just maybe a small question. So I think you kind of mentioned that, but you didn't explicitly explain. So is the sea ice?
I can't hear you, Contemporary.
Can you hear me now? Hello? Hello?
I still can't hear you.
Maybe I'll type.
Maybe you type out the question.
Exactly.
Sorry, Malcolm. I think maybe your speaker's muted. All right. Okay, sorry, it's a problem on that end. Is the sea ice bias also stronger in HH? So I haven't shown a figure for it. I was trying to do it just now, but I couldn't finish it. But so in HH, you can see the surface is both warmer and saltier, and there is less sea ice in the HH, in the Arctic, in both the Labrador Sea specifically, compared to the lower resolution models. So yeah, there's a strong negative sea ice bias in HH, which means the ocean surface is less insulated and you get more air-sea interaction. And as a result, that's Ellis Petit showed for the previous generation of the same model in high-res MIP. So yes, there is less sea ice in HH, yeah.
Yeah, and compared to the CM6 high-res MIP HH, where the sea ice was okay-ish, so it is badly biased low in these pre-industrial simulations, unfortunately. I couldn't tune it up quickly enough and well enough. Anyone else? If not, thank you all very much. There were 3 really, really interesting talks. And I'm sure we'll be at both our upcoming online GA and our GA in January with EERIE. There'll be lots of discussions about these kind of topics and future plans and understanding. And as we get more, obviously, more data from the ongoing simulations, we will have not just 4 eddy-rich models to look at, but 4+3. So that'll be exciting. So then just advertise the next SCS on the 18th of November. And we're going to have 3 talks looking at a range of kind of machine learning topics, looking at causal model evaluation, machine learning atmospheric emulator to look at spin-up, and stochastic deep learning parameterizations for convective processes. So we look forward to that. So Katja and Veronica will be hosting that session. So please join us then. And thank you very much. Bye.